Conversely, when we're cooling water down, that takes a while too, right? Because what has to happen is we have to cool down two water molecules enough so that they can form hydrogen bonds. So we pull some energy out, they slow down a little bit, and they're in a state where they can actually bond to each other. And then we have to pull more energy out to actually create those bonds. So heating water up requires two energy investments, and cooling it down requires two energy withdrawals. Now that's important because we use water all the time to cool our bodies, right? Our bodies are largely water, which is great for maintaining homeostasis. Okay, so let's talk about one more and then we'll bail for the day. Another reason that water is really cool is because ice floats. And water has this really, really unique property of being less dense when it's a solid than it is when it's a liquid. Now we know density causes things to float, right? The less dense an object is, the more likely it is to float. Think about an inner tube. Inner tubes have lots of open space in the middle that's contained by just a really thin piece of rubber. Because it has all that air in it, it's not very dense at all, and it can float right on the top of the water. Basically, ice does the same thing. Ice has this really interesting property, whereas you move from 4 degrees to 0 degrees Celsius, water molecules push out from each other and become less dense. That's why when you put your ice in your Coke, your ice floats to the top. It's actually less dense than the water is. So if you were to take a cross-section of a pond in the middle of winter and measure the temperature of the water, it looks something like this. So this is ice that's completely covering the pond. And we know that ice, frozen water, freezes at 0 degrees Celsius. So at the very top of the pond, that's freezing, that's 0 degrees Celsius. But then as we move down through the water column, water is most dense at 4 degrees Celsius. So as we move down, it goes to 1, 2, 3 degrees Celsius like this. There's nothing else really in the natural world that does that. If you were to take like a block of iron and you were to melt it, and then you were to take another block of iron and drop that in the molten iron, it would sink, right? It would go right to the bottom. But if you were to take ice and melt it, and then a piece of ice and drop it in the melted ice, it would just float right on the top. So ice floats, that's cool, but why is it important in biological systems?
Does it preserve the water underneath?
Okay, very good. What if you're this dude right here, little fish, right? Ice forms and it's more dense than the water. What's going to happen to that ice? Boom, fish death, right? I mean, it's just going to get crushed. Everything that lives in the water underneath it is just going to be smushed. And we know that water is resistant to change in temperatures, right? So this water, or this ice sinks down to the bottom, and then because the water above it isn't changing temperature very rapidly, that water becomes compartmentalized as a solid. It's no longer accessible to biological systems. This process keeps fresh water available to biological processes and doesn't kill the things that are living in the water. Cool? Any questions about that? So we've gone over those two important characteristics. We're going to finish the last three when we come back on Wednesday. I'll see you guys in lab tomorrow. Please, again, remember to read lab 3 before you come.